In this video, we're going to talk about continuity and one-sided limits. So we've seen before graphs that have the same limits everywhere. We know that if we want to find the limit as x approaches 2, we have to go towards x equals 2 from both the left and from the right. And whatever that given y value is our limit. So in this case, we have 4. Also here, even though it's not defined at 2, we're not trying to get to 2, we're trying to approach 2. So we still have a y value of 4. However, even though they have the same limits, they are not both continuous. So continuity and limits are different. Continuity just means we don't want there to be any interruption, any break, any hole in our graph. We want to be able to trace it without lifting our pencil. We can say a function is continuous everywhere or on a specific interval. If we look back here, this guy is continuous everywhere, meaning from negative infinity to positive infinity. The second one here, g of x, is both continuous and not continuous. It's not continuous right here at 2. But if we were to look at a specific interval, like let's say just from 0 to 1, so in the interval 0 to 1, it is continuous. So you have to be very careful that you're specifying your exact interval. If you're looking everywhere, then we would say this is not continuous everywhere because there's a hole at 2. So the formal definition is in this box. This guy's really important. Anytime you're dealing with a free response question, if it says to prove, you must use this definition. These little pluses and minuses, this is how we denote a limit from the right, a limit from the left. That just means as I come in from one direction. If those two are equivalent, that makes sure there's no jumps in our graph. That's basically what has to happen for the limit to exist. If it's equal to the function value, that makes sure there is no hole. So again, basically try to trace it. If you can, then it's continuous everywhere. So here are some examples. This guy right here, my limit exists because as I come in from the left and from the right, they both approach a y value of 4. However, right when x equals 2, that function is not defined. So 4 cannot equal a value that does not exist. So that's why this is not continuous. There's a hole there. If we look at the middle example, here the limit from the left does not equal the limit from the right. As I come in on the left, I have a limit of 4. And as I come in from the right, I have a limit here of 5. And 4 does not equal 5. So it is discontinuous. And then the last one here, we have a vertical asymptote. The limit as x approaches 0 is infinity, and we'll talk about that in the next video. And it does not exist at 0. This never actually hits x equals 0. So because that does not exist, it does not satisfy all 3 of these conditions in this definition. So we have different types of discontinuity, and all this means is that it's not continuous. That's what discontinuous means. It's not continuous. So if it's removable, it looks like a hole in the graph. And if we don't see the graph, we're trying to rewrite our function so that we can define it. So we're trying to factor and cancel. If it's a jump discontinuity, we're going to see a jump in the graph, like right here. We have to jump from one value to get to the next. Factoring doesn't really help us if we're looking at the function. This guy right here is a hole in the graph, so it's removable. Also here, that's a hole in the graph, so it's removable. So here's our first example. Discuss the continuity. So we should remember from previous courses that we do not want the denominator to be 0. So we first need to figure out when the denominator equals 0. And here we see that at x equals 2, we have a discontinuity. That means if I were tracing this thing with my pencil, I would be able to do it everywhere except right at 2. Something happens at 2. So we try to factor to see what exactly happens. So if I factor the numerator, I see that f of x can be rewritten as x minus 3, x minus 2. And if I simplify this, I see that it results in the same graph as x minus 3. This is continuous everywhere. So that means that x equals 2 is removable. And if you look in my resulting function, I have removed the x minus 2 out of the denominator. So just to give you a visual, if I were to type this into my graphing calculator, it would look kind of like this, if that were to. That's f of x. And so again, there's a hole right at 2. If I were to graph the new function, it's going to look exactly the same, only there will not be a hole. And since we're trying to find a limit, we can actually use this resulting function to find the limit of what happens when we get there, even though it's not defined right at 2. Here are some theorems. We're not going to go a lot into these, but if the limit exists, that means that as they come in from the right and the left, they have to be equivalent. If they are, that's the limit. Properties of continuity, again, if we have pieces that are continuous, their sum and differences are still continuous, their product, their quotient, I can multiply it, and the result is still continuous. And finally, the intermediate value theorem. This one is super important, so we are going to elaborate on this a lot later. But basically, as long as we have a continuous function, and we look at any y value in our interval, we have to find at least one x value that results in every single y value. And what that means, intermediate reminds us of the word middle. So if I have an a and a b, and I plug them into my function, and let's say this is f of a, and let's say f of b is down here. If this is a continuous function, I have to be able to draw one point and totally connect it to the other. This theorem is saying when we have this situation, we have to be able to find x values somewhere in this interval that result in every single one of these y values. There's no way to get from here all the way down to here without hitting every single y value in the middle, and we'll look at an application of this. So just as a reminder, in order for the limit to exist, they have to be exactly the same from the left and the right. Here we're approaching 4, both the left and the right, the limit exists. Here it does not exist. And the reason is because the right-sided limit does not equal the left-sided limit. And so here's just a real example of the intermediate value theorem. It does have to be continuous. But again, if we pick any x value in this interval, we have to find at least one y value in that interval. So let's do one example. The intermediate value theorem can be used to guarantee the existence of a 0 or to guarantee the existence of anything. And this is how they'll ask it on the AP test. It's going to use original values of the function. But let's look at this. It says, does the intermediate value theorem guarantee that we have a 0? So first, let's find f of 0, f of 1. So we're going to use the original function value. If I plug in 0, I get negative 1. If I plug in 1, I'll get 1 cubed plus 2 minus 1, or 2. So what the theorem says is that there's no way to get from a y value of negative 1 to a y value of 2. So 0, negative 1, and 1, 2. There's no way to get from here to here without crossing 0. It may go straight, it may be curved, it may kind of look like that, but there's no way to get from a negative y value to a positive y value without crossing 0 at least once. And that's what the intermediate value theorem does, is it guarantees we're going to hit every y value between these two. So not just 0. At some point, it's got to hit 1. And we see that there's no way to draw a line from here to here without having some y value right at 1.